This is the solution to number 4 on the 2014 exam. So we are given that train A runs east-west, and we've got the velocity in meters per minute is given by this function, and it looks like we've got certain values for that function here. And for part A, we're looking for the average acceleration from 2 to 8. So our average acceleration from 2 to 8 would look like this. So our function value at 8 is negative 120, and our function value at 2 is 100. And that's over 6. Which gives us negative 110 over 3, and the units would be in meters per minute, or meters per minute squared. Part B, let's see. We've got this possible conclusion that train A's velocity is negative 100 meters per minute at some time between 5 and 8. So let's take a look at these values between 5 and 8. So we've got v of 5 is 40 and v of 8 is negative 120. And we're told that our function is differentiable, which means that our function also must be continuous, which then means that our function must take on the value negative 100 someplace in between 5 and 8. So let's write all of that down. So part B, so since our function is differentiable, we also have continuity. And we also have the fact that our function value at 8 is smaller than negative 100, which is then smaller than our function value at 5. So by the intermediate value theorem, there must be some value between 5 and 8 that gives us a function value of negative 100. And we're up to part C. Part C starts at t equals 2. Train A's position is 300 meters east of the origin station, and the train is moving to the east. Write an expression involving an integral that gives the position of train A at time t equals 12. Okay, so that's the first part. C, we've got to write an integral that gives the position of the train. So we know that we're starting at 300 meters, and from there between t equals 2 and t equals 12, we can find the total distance traveled by integrating our velocity function. Now for the second part of the question, we've got to use a trapezoidal sum, 3 subintervals, to approximate the position of the train at t equals 12. Okay. So this is approximately equal to, we still have that 300, and now we need to use our table of values. So here are our 3 trapezoids. We've got one between 2 and 5, then between 5 and 8, and then between 8 and 12. So the first trapezoid, the height is 3, and then the bases are 140. So the height is 3, and then the bases are 140. Second trapezoid, it looks like, again, the height is 3, but the bases are 40 and negative 120. And then the last one, the height is 12, and we've got negative 120 and negative 150. So times 4, and then negative 120 and negative 150. Okay, so let's work on simplifying all of this. We've got a 300. This is 170, or 140 divided by 2 is 70, times 3 is 210. This is negative 80 divided by 2 is negative 40, times 3 is negative 120. And then our last term here looks like negative 270 times 2. So 510 minus 660 is negative 150. Okay. Oh, so that is our approximation for part C. So what does that mean in terms of position? That means that train A is 150, what are we in meters, west of our train station at 12 minutes. Okay, last part, part D. Now we've got a second train, train B, traveling north from the same station, and now we're given a function for train B's velocity, and we're given a position at t equals 2. Now I've got to find the rate in meters per distance at which train A and train B is changing at t equals 2. So we have a situation where train A is going east-west and train B is going north. So the distance between them we'll call C, and the relationship between all three sides of our triangle is given by the Pythagorean theorem. So we've got a squared plus b squared equals c squared. And there are the derivatives. We've got 2b db dt, whoops, db dt equals 2c dc dt. We can cancel out all of those 2's. And we're looking for dc dt. That's the rate at which the distance between A and B are moving away from each other. So we need a value for C, for B and dB dt, and for A and dA dt. Now remember, this is happening when t is equal to 2, and they tell us right here that B is equal to 400 meters. So let's enter that in. And in part B, they told us, is it part B? No, it was part C. They told us that at t equals 2, train A's position is 300 meters. So we'll put a 300 for A. So now if this distance is 300 and this distance is 400, we know that this distance should be 500. Now we have to fill in our rates of change. So dA dt we can get from the table. At t equals 2, dA dt is 100. Now we need to find dB dt, right? That's the rate of change for train B. And they gave us this little function right here. So let's plug in 2. So So we get negative 5 times 2 squared, so negative 20, plus 120 plus 25 is 125. So that value goes right there. Okay, now we're just solving for dc dt. I'm going to make life a little easier, and I'm going to get rid of a bunch of zeros. Just get rid of that and that. So now we've got 3 times 100 plus 4 times 125, that's 500, equals 5 dc dt. This is what, 160, and that's in meters per minute, is equal to our dc dt. And that's it for part D.